Welcome to this SEM tutorial. Today's tutorial will be an introduction to molecular dynamics, and this is mostly directed towards chemists who are already familiar with traditional approaches in computational quantum chemistry, where the goal is often to do things like predict spectra or predict reaction energetics, and this is then done using static methods like geometry optimizations, frequency calculations, and transition state searches. In this tutorial, I will outline how to produce the same things, only using molecular dynamics instead of static approaches. I've already mentioned these two goals, spectra and reaction energetics. Today I will focus only on the former, and more specifically on IR spectra, and I will leave the discussion of reaction energy profiles to another day. So I will start with just the standard static procedure to compute an IR spectrum, which I assume most people will be familiar with. The general approach is first to optimize the geometry so that we are firmly at the minimum of a potential energy well, and then once there, adopt the harmonic approximation, so assume that the well is harmonic in every direction and compute the frequencies. So let's very quickly demonstrate how this is generally done. Let's start by drawing a water molecule. And then we can decide on the model we want to use to describe this water. And let's select DFTB and then GFN XTB. This is an electronic structure model, but it's a very fast one. Now we want to do, as previously discussed, a geometry optimization, followed by a frequency calculation. So that's it, we are already set up. Let's save this input file. Let's run. Now the calculation is already done, and we can look for the IR spectrum using Spectra. As you can see, 3 peaks were computed. They correspond to 3 different modes. The peak on the right is a bending mode, and the 2 peaks on the left are both stretching modes. This is symmetric and this is asymmetric. So all that is left now is to export the spectrum so that I can use it outside of AMS. And that's it. We are done. We have managed to compute the IR spectrum in the harmonic approximation in about 2 minutes time. Now let's say we would like to compute an IR spectrum using molecular dynamics. Why would we want to do this? Well, because there's a strong disadvantage, namely that it's much slower than the previous approach, but it has the disadvantage that it captures anharmonic effects. So if the potential energy well is very dissimilar to a harmonic well, then this approach will give us a different spectrum and it will be better. So let's review what molecular dynamics is very quickly. So we will propagate the system using Newton's equations of motion. What we have is the coordinates of the system at the bottom of the potential energy well, and we assign the atom's starting velocities that correspond to our desired temperature, which is here 300 Kelvin. Our first step in practice is to equilibrate our geometry at the desired temperature. Why do we need to equilibrate? Well, we are at this moment sitting at the very bottom of a potential energy well because we optimized the geometry. And if we now start to do a molecular dynamics simulation without a thermostat, we assign velocities, so the atoms would by definition start to move, and the average potential energy would go up, as you can see in this example simulation. So that energy, the potential energy, has to come from somewhere, so the kinetic energy has to go down. And since the kinetic energy originally corresponded to 300 Kelvin, it will now be too low. So the only thing to do is to keep adding velocity to the system until the system finally finds its equilibrated state, where it has an average potential energy and an average kinetic energy that corresponds to 300 Kelvin, and the average potential energy that goes with that. So what we need to do in practice is we add a thermostat, and the thermostat is just a way to keep changing the velocities of the system, of the atoms, to keep adjusting the velocities of the system if they become too small, or of course if they become too large. So after we have done that, after we have equilibrated the system at our desired temperature, we can start running the production simulation, the actual simulation from which we can afterwards extract the IR spectrum. This is a simulation that we have to run without a thermostat. Since the system is equilibrated, it won't matter that there's no thermostat. The system will now stay at the desired temperature. The reason we have to remove the thermostat is because for the IR spectrum we have to look at the dynamics of all the atoms, and a thermostat will always disrupt the dynamic. And then in addition, we need to store every step so that we can follow the motion of the molecule in high resolution. And then finally, after we have done this simulation and stored the trajectory, we can get the IR spectrum by analyzing this trajectory. What we have to do now is we have to compute the dipole moment autocorrelation function, which is this equation here, which, as you can see, features the time derivative of the dipole moment at every time step, and then we need to Fourier transform that. So these are the 3 steps we have to take, and I will show you how to do that with our software. We still have our optimized water molecule from before, and now we want to start with equilibrating this structure at 300 Kelvin. So now we select molecular dynamics, no more frequency calculations, and we have to set some settings. A step size of 0.5 femtoseconds is enough for this approach. And I would like to equilibrate for 10 picoseconds, which corresponds to 20,000 steps of 0.5 femtoseconds. Sample frequency, this means that the coordinates are stored every 100 steps, which is fine. And well, the initial velocity is random, but corresponds to 300 Kelvin. And since we are equilibrating, we have to add a thermostat, and it's just an equilibration, so we can add a crude thermostat, which means we select Berenson at 300 Kelvin with a strong damping constant of 100 femtoseconds. So we are done, and we can save this input. And run. Now we have to wait a little while. And 20,000 steps later, the simulation is done. This took about 10 minutes on my machine, and this should be now our equilibrated water molecule. So let's open this in Am's movie to look at the trajectory. And we can see from the energy, from the potential energy, that indeed the system has been equilibrated. You see it equilibrated to a higher potential energy than where it started, which is what we expected because we started at the very bottom of a potential energy well. Now, we can also look at how the system moves, and well, what we see is basically that there's nothing strange with this equilibration. It looks fine. Another thing that we can check is the temperature of the system, and indeed, as we would like, we see that the temperature basically oscillates around an average value of 300 Kelvin. So the system has been successfully equilibrated. So that now means that we can continue on to the production run, which is the run that we will finally use to extract our spectrum. So let's start with putting some settings in the molecular dynamics section. Most things remain the same, but for example, a change that we have to make is we have to sample every time step now, because we are interested in the motion and the vibrations of the atoms. In addition, as I mentioned before, we have to remove the thermostat in order to not interfere with the motion of the atoms. 20,000 steps or 10 picoseconds is fine for our goal. So let's save this setup. And let's not forget that we have to restart from the velocities of the final snapshot of our equilibration. These velocities already correspond to the structure, because what you see here is the final geometry from the equilibration. So we are ready to save and to run our production run. Another 10 minutes later, the simulation is done. And so let's look at the trajectory in AMS movie. Okay, so we can see now that the potential energy has remained stable. Let's zoom in a little bit on the water molecule to see what it looks like. If we look at the temperature, we see that also the temperature remains stable at approximately 300 Kelvin. Okay, so now we need to compute the IR spectrum, and for this we first need to compute the autocorrelation function. So for that we have to open the menu under the MD properties heading, and we would like to use every step in the trajectory. That's why we stored all of them. We want to compute the autocorrelation function for the dipole moment, because that's what we need for IR. We want it to be normalized, and we want to use the time derivative, though this is not crucial. We get similar results with or without the time derivative. And finally, as the maximum number of steps used for the autocorrelation function, I use half of the total number of steps in the simulation. So now we are ready to generate the autocorrelation function. Now, upon generation of the autocorrelation function, which is the strongly oscillating upper graph, the Fourier transform of it is automatically produced, and that is the IR spectrum. And as you can see, we have again 3 peaks. Let's zoom in a little bit on the peaks. And this reveals that the spectrum looks at first sight quite similar to the harmonic spectrum. So we're done. Let's export the spectrum so that we can compare it to the harmonic result. And with that we are finished. We have computed successfully an IR spectrum. It took us around 30 minutes to compute this spectrum, and as you can see it looks very, very similar to the spectrum we computed using the harmonic approximation, but we know that this one is better. For a small molecule, computing IR spectra using molecular dynamics has the advantage that it provides some additional accuracy, but this molecular dynamics based approach really comes into its own for bigger systems. Let's take as just an example an aqueous system, in fact just liquid water. Say we would like to compute the IR spectrum of something in liquid water or of this liquid water itself, then the standard procedure is no longer an option. Of course, we can follow the standard procedure, but the result is not reliable. And the reason is that for a complex mobile system such as this, the potential energy surface is extremely rough and one single state consists of many, many small, shallow potential energy wells. And all these shallow wells contribute to the state of the system. So minimizing it into the minimum of one single well is not representative for the full state. So we need a way to explore, and that is what we have molecular dynamics for. Now the procedure for computing an IR spectrum using molecular dynamics for a system such as this is exactly the same as it is for a small molecule. The only difference is of course in the setup of the larger system, which we will go through now. Okay, so let's build us a water box. Let's build a nice and small box with an old-fashioned number of 64 water molecules, and you can see that of water, and you can see that this gives me approximately the correct density. So let's create it. Here we are. And now let's set up our simulation that will ultimately lead us to an IR spectrum. Now I would like to, the plan is to get a spectrum that we can compare to the spectrum for the single water molecule. So we should use the same approach, but that's slow. An electronic structure method for a system this big is very slow. So let's start and do a pre-optimization with the force field. Select ReXFF, do a geometry optimization. We select a force field, and we still have to mention that this is a periodic system. And I think that is pretty much it. Let's save this input. This is just an initial optimization so that we are sure that there are no strange clashing atoms in this system. Wait. No, this is it. Let's run. This is a run that is fast enough to wait for. So here we are. We have optimized our geometry. Now the next step is to do the same thing with the GFN XTP model, where no further settings are required, so we can save this setup. And ultimately run a geometry optimization. Now, with this will take a few hours on my machine, so we cannot wait for it. But the steps after that are exactly the same. The steps after geometry optimization, when we are sure we are in a local minimum somewhere, are exactly the same as they were for the single water molecule. The system had to be equilibrated using a thermostat, then we needed to run a simulation without a thermostat and store every time step, then compute the dipole moment or autocorrelation function and Fourier transform it. After doing these three things, we would have spent approximately a day of computations, but we have obtained a spectrum that cannot be obtained in any other way. In summary, I have demonstrated how to produce IR spectra from molecular dynamics for small molecules. This provides additional accuracy on top of the harmonic approximation, but it's quite hard to predict for which molecules this is important. And in addition, I have demonstrated that we can produce IR spectra from molecular dynamics for large, complex systems like liquid water. And in this case, the importance of this approach is more obvious and more general because there is no other way. I hope you found this video useful. Thank you for watching. Bye.